So today we are going to discuss about the space observations of geosphere, biosphere, atmosphere interactions and climate. As we know, climate is one aspect which the present day world is mostly worried about, mainly because we know that because of there are several processes in the atmosphere, which is basically through the geosphere, biosphere and atmospheric interactions. The climate is, there is a change in the climate, and we are worried about the sustainability of our Earth atmosphere climate, the climate system as a whole. So today we discuss about how space observations are useful in monitoring the geosphere, biosphere, atmosphere interactions and climate. So I am from the Space Physics Laboratory of Vikram Sarabhai Space Center of ISRO. We're located at Trivandrum. We at Space Physics Laboratory works on all these aspects, working on the geosphere, biosphere, atmospheric interactions. Basically, we have a set of ground-based observations using radars, LiDARs, SODARs. And we use high-altitude balloons and rockets, in addition to a suite of satellites, both international satellite data as well as our own ISRO satellite missions data, for understanding the geosphere, biosphere, and atmospheric interactions, which has relevance for the climate assessment. So, while talking about geosphere, we know that geosphere refers to the solid Earth, including the crust, mantle, and core. There are several geological processes which are relevant to the climates. The most important one is the volcanic activity. And of course, the earthquakes are also important geological process, but it doesn't have any direct implications on the climate. But other processes like weathering, formation of landforms, these are all affects the important role in the geosphere atmospheric interactions. One typical example is actually the volcanic activity. We know that the recent past, we have the Pinatubo eruption and El Chichen eruptions, and these eruptions, it was reported that there was significant reduction in the surface reaching solar radiation because of the blocking of radiation by the particles emitted from these volcanic eruptions. This is a classical example of how the geological processes can affect the climate, and these are all long duration processes. Like that, the biosphere, when it comes to biosphere is relatively a thin layer of Earth's surface that supports life. And we know that there are several biospheric processes which emits gaseous species as well as particles into the atmosphere, which are also very important for the sustainability of our system. Basically, it can affect the climate. And when it comes to the geosphere, biosphere, atmospheric interactions, one of the most important aspects is the carbon cycle. We know that the exchange of carbon dioxide between the atmosphere and the biosphere and the geosphere is central to the global carbon cycle. In addition to that, there are weather and climate processes. We know that atmosphere influences the weather pattern and long-term climate, and atmosphere in turn affects the change in the atmospheric composition is also very important. Both geosphere and biosphere releases gases and aerosols that impact the atmospheric composition, and it affects the radiation balance. And the reverse process, like the way in which geosphere and biosphere affects the atmosphere also affects the geospheric processes. We know that the temperature and precipitation, the high temperature and precipitation process influence the rate and type of weathering and erosion processes in the Earth's surface. These are also very important for when we talk about the geosphere, biosphere, atmospheric interactions and climate. And perhaps one of the most important aspects is the anthropogenic activities. We know that the present changes in the climate is basically due to the anthropogenic activities, which are basically the human-induced actions that have significant impact on geosphere, biosphere, as well as the atmospheric processes, and which are very crucial to the Earth's ecosystems, and it can affect the climate and the environmental balance as a whole. So when we coming to the geosphere, biosphere interaction and climate, one fundamental understanding which we should have is on the radiation balance. We know that basically the energy balance of the Earth atmospheric system is controlled by the solar radiation which we receive from the sun, which is at a temperature of photospheric temperature of around 6,000 degrees Celsius. And we know that the mean Earth temperature is around 15 degrees Celsius. And the solar radiation is basically, we know, which is around a few 100 nanometers to about 4 micrometer or so, and peaks at in the visible region, and which is basically the consequence of the Planck's radiation law. We know that according to the Planck's radiation law, a body which is at 6,000 degree Kelvin have a peak emission at around 500 nanometer. Similarly, the Earth, which is at 15 degrees Celsius, emits radiation in the terrestrial wavelength, which is around 10 micrometer, and which shows that we receive radiation in the short wave regime, whereas the Earth emits radiation in the long wave, which we call the terrestrial radiation. So for a sustainable system, there should be a radiation balance between the short wave radiation which is received by the Earth atmospheric system and the long wave terrestrial radiation which is emitted by our system. So this is a classic picture from Trenberth et al. 2009, which shows the radiation balance of the Earth. We know that we receive around, at a given time, we receive around 341 watts per meter square of energy, and Earth has a mean albedo of about 30%, which reflects about 102, almost 100 watts per meter square radiation back to space immediately. And rest of the energy, which is used in different processes in the atmosphere and the Earth's surface, and finally, which leads to a mean temperature of 15 degrees Celsius, and Earth emits radiation in the long wave. And there should be a balance between these two, which I have mentioned some time back. And any disturbance in this balance, any deviation from this balance lead to climate change. So one of the most important aspects when we talk about the radiation balance is the atmospheric composition. We know that the major constituents of the atmospheric composition is basically atmosphere composed of nitrogen and oxygen. The nitrogen, which is around 78.1%, and oxygen, which is around 20.9%, which shows that almost 99% of the Earth atmosphere consists of nitrogen and oxygen. But the rest of the 1%, almost 9.93% is argon. So we know that the atmospheric trace gas which is actually the greenhouse gases and other trace gases like ozones and other important carbon monoxide and so forth, water vapor, carbon dioxide, methane, nitrous oxide, ozone, and several CFCs which comes from the human activities. These are all composed of only 0.1%, but though it constitutes a very small fraction of the atmosphere, it plays a major role when it comes to the climate. We know that in addition to this gaseous component, the geosphere and biosphere processes emits so much of particles into the atmosphere known as aerosols. We know that these are solid and liquid particles of different composition. These particles are also very important, which is in the in the interaction with the radiation and affecting the radiation balance of the Earth atmospheric system. So we know that there are different radiative processes. These radiative processes are which decides how the radiation propagates to the solar radiation propagates through the atmosphere, as well as the terrestrial radiation which emit and escape to the space also. And we know that it involves the ionization of atoms, photodissociation of the molecules, the vibration excitation of the molecules, and the rotational excitation, and depends on these processes vary, and accordingly we have different spectral distributions and processes. In addition to that, the particles present in the atmosphere as well as the gaseous molecules which scatter radiation. So finally the outcome is actually, if you look at the spectral distribution of the solar radiation which is received at the top of the atmosphere as well as at the surface, if we examine, we can see something like this, as shown in the figure, which is actually published in a recent article in Atmospheric Measurement Technology. If we look at this, we can see that what is the role played by the extraterrestrial. This is basically the solar atmosphere as well as our Earth's atmosphere in the transmission while radiation passes through the atmosphere. There are very strong absorption bands due to water vapor and carbon dioxide, even in our short wave, as well as there are some sharp lines. And there is this overall reduction in the intensity which is basically due to the atmosphere, because atmosphere, we know it is scatter and absorbs the radiation, and there is a significant reduction in the solar radiation reaching in the surface. This scattering and absorption is very important for the radiation balance, which is mainly due to the atmospheric composition And this atmospheric composition is mainly controlled by the geosphere and biosphere processes. So I have mentioned to you about the solar spectral distribution of the solar radiation. This is a picture which I have taken from the website, NASA website, basically from the Clouds and Earth Radiant Energy System project. This is an excellent, long-term database which is available for the international scientific community. This is the seasonal variation of the solar radiation at the top of the atmosphere. This is the net downward radiation at the top of the atmosphere. We know that solar radiation, which enters the atmosphere through different processes, will happen through scattering and absorption, and certain amount of radiation will reflect it back. And finally, we can calculate the net radiation. If you look at, see that mostly solar radiation is focused, at the tropical region, which as we have expected, and then there is a distribution towards the pole. And this redistribution, this is the one which determines the circulation, the atmospheric circulation, and the climate processes. So essentially, when we say the overall radiation balance, it should be balanced, that the energy which it receives by the Earth atmosphere system should balance the energy which is either reflected or emitted, and it should be ideally zero, the balance. So when we talk about the climate, which is due to the disturbance in the radiation balance, we need to look at certain variables. These are called essential climate variables. The essential climate variables are basically the physical, chemical, or biological variable, or a group of linked variables that critically contributes to the characterization of the Earth's climate. The importance of this is actually when we look at this, there are several climate variables which are required to understand the climate state as a whole, and to monitor and have the mitigation strategies. So the space-based observations are the best way of looking at it in a global way as well as in the regional way. And if you look at some of the most important essential climate variables, which I will discuss here, the first one probably will be the surface temperature, which we are worried about. We have a long-term measurements of surface temperature now, which shows an increasing trend. We all know that, which we call it as global warming. And the surface temperature monitoring in a global way, it's very important. So this has to be measured at various altitudes from the surface to track the changes in the global and regional temperature. Another most important parameter, perhaps, in the essential climate variable is the sea surface temperature. So sea surface temperature is basically the temperature of the ocean surface, which is essential for understanding ocean circulation and climate patterns. We know that there are international missions. Our own Indian missions, like OceanSat series, has the capability to measure the sea surface temperature. Then the sea ice extent, the snow cover, glaciers and ice sheets. These are all very important, cryospheric conditions, which are very important for essential climate variables, because this hold mostly the water content. Mostly the water is reserved in these forms, and which decides this sea level. And the measuring changes in global mean sea level rise is actually, sea level is a very important thing. It is basically done using different space-based observations. And this gives very good understanding that how the global climate is affecting in the future. The sea level rise is one of the most important aspect in the essential climate variables which we need to look into. Then when it comes about the parameters which determines the surface, these parameters is the ocean acidity. We know that the tracking the acidity of ocean due to the absorption of carbon dioxide is an important factor which controls the climate and the amount of greenhouse gases in the atmosphere. It is very important to monitor the presence of greenhouse gases like carbon dioxide, methane, and nitrous oxide. These are the important greenhouse gases, which leads to warming in the atmosphere. At the same time, we know that the particles like air, which known as aerosols, a significant portion of the aerosols like sulfate, nitrates, which scatter radiation back to space, which controls the warming and leads to a cooling. And this combined effect is the one which decides the global warming. In addition to, we know that the importance of ozone. It is very important to measure and monitor the distribution of ozone concentration. In fact, the ozone hole, it was in a quantitative way, it was determined because of the space-based observations in the later stages, in the later 70s. using the international missions like TOMS and OMI, which gives very clear idea about the ozone. And we know that it is now very important to have precipitation measurements in a global as well as regional way, humidity, wind speed and direction. Our OceanSat gives very good data about wind speed and directions. Then cloud properties, radiation, land cover, land use changes, the fire disturbances in the surface system, river discharges, permafrost, terrestrial carbon, and marine productivity. And there are several other things also. These are very important essential climate variables which we can monitor from space also. And ISRO has made conscious efforts in this direction. Our NRSC has a Bhuvan portal to exchange this data to the public community, and we can use it for different climate-related studies. So, but one important thing is that when we talk about the climate, these essential climate variables, like all these climate variables cannot be measured using a single technique or single platform. No single satellite cannot. We have to have a chain of satellite observations, both our ISRO satellite as well as international satellite working together only can be addressed this in a holistic way. And the international scientific community is putting a lot of effort in this direction. Now, some of the most important international space mission for climate studies are because the space missions play a crucial role in climate studies, which provides very valuable data and observations that are essential for understanding the Earth's climate system and for monitoring the climate change. So the most important one, probably the NASA's Earth Observation System. It is a series of satellites launched by NASA. It includes missions like Aqua, Terra, and Aura. We all, probably some of you may be using the moderate resolution radiometer like MODIS, which gives some of the most important essential climate variables such as sea surface temperature, land surface temperature, and most importantly, aerosols and greenhouse gases and ozone. And the European Space Agency is having the Copernicus Sentinel missions, which is also a series of satellites. We know about Sentinel 1, 2, 3, and 5 missions, which are very relevant for climate studies. And the Global Precipitation Mission, which is actually a joint NASA JAXA missions, which is a constellation of satellites to measure global precipitation, which is very critical for understanding the Earth's water cycle. And when it comes to our ISRO's missions, we also have a series of satellites like INSAT and INSAT 3DR. These are advanced weather satellites which provide high resolution observations of Earth's atmosphere, which includes cloud cover, water vapor distribution, and temperature profiles, which are very crucial for climate and weather research. We know that we have the IIRS series, Indian Remote Sensing Satellite Series. IIRS series consists of several satellites equipped with the various sensors that enable to monitor land use, land cover, and vegetation health and forest cover changes. And we have an OceanSat series. We have OceanSat 1, 2, and 3, which are dedicated to ocean monitoring and provide essential data significantly to the ocean atmosphere interaction and very important for understanding the climate variables. We have a ResourceSat series. We have already ResourceSat 1 and ResourceSat 2, which are designed for land and resource management. This gives data on land cover, land use, and vegetation changes, which are relevant for climate studies. So these are all some of the important space missions which are relevant for climate studies. With all these missions, including space missions and ground-based observations, what is our current understanding? We know that we have an agency called Intergovernmental Panel on Climate Change, IPCC, which is under the control of United Nations, which gives, the current observed warming rate. The observed warming is driven basically by the emissions from human activities, which is the current understanding, with the greenhouse gas warming partly masked by the aerosol cooling. And this is the latest report which released in 2021 says that we have around the observed warming, which is in the last decade relative to 100 years back, which is around 1 degree Celsius, which is actually the combined effect of the warming due to greenhouse gas emissions as well as the cooling due to aerosols. So very important to understand the warming effects. The major factors behind the warming, which is how the greenhouse gases are emitted in the atmosphere, basically the carbon cycle, as well as the aerosols. In addition to that, it's very important to understand the land use, land cover changes, which decides the reflectance of the overall albedo of the Earth atmospheric system, which is also a major factor controlling the climate. So if you look at this, this is a global mean pattern, and the uncertainty to how clear, to have mitigation strategies we need to put in place. So for that, if you look at one of the key component of the global warming is the carbon cycle. Basically, it's the carbon dioxide in the atmosphere. We know that the carbon dioxide in the atmosphere is basically showing an increasing trend. We know that the Keeling curve, which is basically the long-term measurements of carbon dioxide from the Mauna Loa Observatory, thanks to the Scripps Institute for Oceanography and the NOAA for maintaining such a long-term observation. This is actually an excellent observation set for the global community to understand how the CO2. Now, there are efforts all over the world, even from our Indian side, for these measurements. We will discuss about that now. This carbon dioxide in the atmosphere is basically controlled by different processes like photosynthesis, which we all know, the respiration processes. We know that all living organisms undergo respiration, including plants, which emit carbon dioxide into the atmosphere. While photosynthesis take carbon dioxide inside, the respiration process gives out the radiation, means to the atmosphere. There are processes like a decomposition, where the plants and animals, when it die, they undergo decomposition, and during this process, carbon is really liberated into the atmosphere. We know one of the most important processes is the fossil fuel. We know while fossil fuel formation, a lot of carbon is stored in the formation of fossils. But when we use it for our anthropogenic activities, so much of carbon dioxide is released into the atmosphere. And all this atmospheric carbon is always controlled by the ocean absorption. The ocean phytoplankton, which takes carbon dioxide for its food chain, which absorbs, and there is a process called the carbon sequestration, and which increases the ocean acidity, which is another important aspect for the oceanographic studies. But overall process is actually which decides the variation of carbon dioxide in the atmosphere. It's very important to have space-based observations to understand it in a global way. And then the question comes is that how space-based observation can be used for understanding this carbon cycle. The most important one is the monitoring of the greenhouse gases. While doing the greenhouse gas monitoring, we will have how much it has made the changes, satellite mapping of the carbon sources and sinks, then of course the deforestation and land use changes from the satellite data, forest monitoring from space, then oceanic carbon uptake and estimation from satellite data, space observation of wildfires and biomass burning, then carbon flux estimation from satellite observations. Combining all this, through all these efforts, we can have space-based observation to understand the carbon cycle. So at present, there are few space missions. We all know that there is an excellent mission called Orbiting Carbon Observatory, which is basically an international mission, which is in a polar orbiting satellite, which is now, which was launched in 2014, which gives in the public domain so much of the data on the CO2 emission into the atmosphere. Now there is a follow-up is also in place, which is launched in 2019, OCO3, which is in the International Space Station. The advantage of this is actually which give more frequent global coverage. There are other missions like GOSAT, Greenhouse Gases Observing Satellite by JAXA, which also provide, there are some of the vital information on carbon dioxide, methane, and this database is also available to the community. There is a NASA initiative called the Carbon Monitoring System, which is actually a multiple satellite mission, data from multiple satellite missions, aircraft campaigns, and ground-based observations put together to monitor and assess carbon sources and sink, including land use changes, and other components also are included. This also gives very important information in a global way. Little bit on the OCO2 observatory, the orbiting carbon observatory. This is basically a spectrometer which measures the reflected sunlight from the Earth's surface at specific wavelengths from a given location. We know that it is CO2 is in a polar orbiting so that it can give the global coverage. The gaseous molecules like greenhouse gases, like carbon dioxide present in the atmosphere, which absorb sunlight at specific wavelengths. So the received signal at the satellite spectrometer can be analyzed to get the information on the carbon dioxide molecule present in the atmosphere. Of course, the meteorology is quite involved process, and it can give very valid information. If you look at this graph, which is published in Science in 2017 or so, which gives a global coverage of carbon dioxide for different periods. We can see the seasonal changes on a global basis. If you take some of the specific region, we can have the measurements on long-term as in the Keeling curve. And we can see that it goes excellent matching with the ground-based observations. So these space-based observations can give excellent results on the carbon dioxide, which has now already proved. And we have a project in ISRO called ISRO GBP's National Carbon Project, basically to assess the carbon pools over the carbon pools, fluxes, and net carbon balance of the terrestrial biosphere over India. The main objective was to establish an observational network, which is now in place, and combining this with the remote sensing-based spatial databases and modeling. ISRO is making periodic assessment of the carbon balance. Then estimating the sources and sinks of carbon dioxide across the Indian ecosystem is also one of the important objectives of this program. Then this will assess the terrestrial and vegetation biomass in the country using ground sampling as well as remote sensing data, which generate very excellent geospatial data on the terrestrial phytomass and terrestrial carbon. So the effort is mainly aimed at improving our understanding of the carbon budget for the Indian region, which will be an important input to the global science community as well through satellite and in situ observations. Some of the ISRO satellites which are very important for this effort are the OceanSat series, which I have mentioned some back. We know that the OceanSat series, the OceanSat 1, 2, and 3, which is basically designed to monitor oceanographic parameters, but they provide very valuable sea surface temperature, ocean color, and ocean parameters, other oceanic parameters, which are very important for studying the ocean, productivity, which can give important information on the ocean's role in carbon dioxide uptake and distribution. Then our land, we have ResourceSat series, which is actually a multispectral cameras, which can provide important information on land cover, land use changes. This is very important for monitoring changes in the forest cover and deforestation, which is a very crucial parameter for understanding the carbon sources and sinks. We have Cartosat series. These are all images. These images will be used for land cover mapping and change detection. This data is also valuable for tracking changes in vegetation and land use, which affect the carbon cycle. So these ISRO satellites are also we use for this carbon cycle studies. Now, I have mentioned when we have the carbon cycle is very important for controlling the amount of carbon dioxide in the atmosphere, which leads to the warming in the atmosphere, which I have mentioned some back while talking about the IPCC assessment. But this warming is controlled by the cooling, the net cooling by the aerosols. But one important aspect of the aerosol effects on in the geosphere biosphere process is actually the emission of aerosols into the atmosphere. We know that there are several geosphere processes which emit so much of dust into the atmosphere, like volcanic dust into the atmosphere. Then there are processes like sea surface processes which emit sea salt into the atmosphere. Anthropogenic activities, wildfires, both are natural as well as anthropogenic, emit tons of aerosols into the atmosphere at every time. These particles, which are in the atmosphere, which interacts with the solar radiation, which I talked to you in the beginning, because we have the short-wave solar radiation receiving from the sun, and this radiation is one of the main energy source for driving the atmosphere as well as the climate system. But the aerosols present in the atmosphere can disturb the amount of it can reduce the amount of radiation reaching the surface. There are different types of aerosols like sulfate, ammonium, nitrate, sodium chlorides, trace metals, carbonaceous aerosols. We know that all these are different chemical species having different dielectric properties and hence different refractive index. So these aerosols most of them can scatter radiation back to space. But there are certain critical aerosols like a black carbon aerosols which absorbs radiation, which complement the global warming. So very important to understand the aerosols in totality. What are the type of aerosols present in the atmosphere and how it is well distributed. So I have mentioned that aerosol basically of two types, scattering aerosols and absorbing aerosol. Absorbing aerosol lead to, scattering aerosols lead to cooling in the atmosphere, whereas absorbing aerosols lead to warming. And these aerosols or the greenhouse gases present in the atmosphere induce an effect which is called the radiative forcing. Radiative forcing is basically the change in the net radiative flux, which can be either in the long wave or in the short wave at the top of the atmosphere due to the external perturbation. If it is due to greenhouse gases, we call it as greenhouse radiative forcing, and which is basically the basis of global warming. But when it's due to aerosol, we call it as aerosol radiative forcing. It can either warming or cooling. So the geosphere and biosphere processes leads to emission of greenhouse gases as well as large amount of aerosol into the atmosphere, and which decides the radiation balance. So to understand that, we need to have certain parameters, especially for aerosols. One of the most important parameter is the optical depth. The measurement of optical depth, basically the total optical depth and then the aerosol optical depth. Then I mentioned that it leads to scattering and absorption. So depend on the type of aerosol, it can, some of the aerosol leads to scattering and some of them leads to absorption. So there is a parameter called the single scattering albedo, which decides aerosol leads to, lead to cooling or warming in the atmosphere. Then of course the scattered intensity have a complex distribution in the atmosphere, which is decided by the phase function. So all these parameters are climate relevant parameters, which we need to have observations using both ground-based and space-based observations. So there are certain mechanisms. I mentioned that aerosol lead to the scattering and absorption, which we call it as direct effect. When solar radiation reaches the earth, interacts with the aerosols and greenhouse gases also directly, and a large amount of aerosol means large amount of radiation scattered back to space by aerosols lead to cooling. But at the same time, the greenhouse gases absorbs lead to warming. So the net effects decides the net temperature, and their direct effect is one of the most important things. In addition to that, we all know for the clouds to form, there should be a surface where aerosol act as the surface for the clouds to form, which we call it as cloud condensation nuclei. If there are no aerosols in the atmosphere, there won't be any clouds. So for the clouds to form, we need to have aerosols in the atmosphere. However, if there are more aerosols in the atmosphere, the amount of cloud formed means that the size of the droplet size will be small, and this leads to increase the cloud droplet concentration, and these clouds will be more brighter. So brighter clouds reflect more radiation back to space, and which will lead to a cooling in the atmosphere. So we know that if there are no atmosphere, we know the Earth would have been a very cool, which is the atmospheric temperature will be of the order of minus 30 degrees Celsius also in the global mean. But the atmosphere play a major role. So we need to have a finite warming in the atmosphere. But if there are the more cooling in the atmosphere also is actually can have significant climate change. So the more aerosols in the atmosphere can leads to certain areas enhanced cooling due to an effect called the first indirect effect, which is actually a Tommy effect, which the person who the first to propose this effect. Another effect is actually the increased cloud lifetime. When there are more aerosol lead to more smaller droplets and more cloud droplets, it will suppress the rain. So which we call it as second indirect effect, which is also a climate impact. Recently, based on observation in the South Asian region especially, we have in the scientific community has come out with a new effect called the semi-direct effect, which is basically the cloud burning due to the atmospheric heating by aerosol present inside the clouds. These are some of the most important effects which we need to address. See, if you look at the global distribution of aerosols, we can see that this is the way one particular season aerosols are distributed from. This is a global map of aerosols. Basically, the parameter is called aerosol optical depth from the MODIS satellite, which we can see that the tropical region aerosol presence is quite significant. All the areas where monsoon is active, where aerosol presence is also quite significant. Naturally, we can have a thinking that the regional climate like a monsoon circulations can be affected by the presence of aerosols. So in this context, ISRO has formulated another program like National Carbon Project called Aerosol Radiative Forcing over India project, where we have a network of aerosol observatories over India. We conduct specific campaigns to address some of the specific processes related to aerosol forcing. In addition, I have mentioned some time back, we have Indian remote sensing satellite series, which provide valuable data on aerosols, in addition to the international satellites also. We assimilate all this data and formulate aerosol models, which is very important for radiative transfer computation. The final outcome is actually the estimation on the regional radiative forcing. This is very important for the assessment of the solar energy available for our different energy needs. This is one of the most important energy sources now recently we talked about. And another important impact of aerosols recently, which we mostly worried, are actually the deposition of absorbing aerosols on the Himalayan glaciers. Indian scientific community is working on this particular aspect in the recent time. There are several scientific results also on that. The absorbing aerosols depositing on the Himalayan snow and glacier region can affect the health of the Himalayan glacier, snow especially, and this also can have our regional hydrological balance, impact on the regional hydrological balance. And the presence of aerosol, I have mentioned some time back, in the atmosphere definitely will have an impact on the radiation balance. And we know that we have the regional climate process like monsoon circulation can be affected due to the presence of aerosols. So it is very important to have accurate observations on aerosols over our region. In this process, I mentioned about the network of observatories. This network of observatories are mainly distributed all over the India, operated with the support of the national institutes and the universities. We have several measurements like aerosol optical depth using our in-house built multi-wavelength radiometer. This is placed at all these observatories, which make measurements on aerosol optical depth. In addition to that, we make measurements on black carbon mass concentrations and scattering coefficients of aerosol, basically the scattering nature of the aerosols, which is very important while talking about the cooling effect of aerosol, then the amount of aerosol, the total amount of aerosol, the chemical composition, then the radiation at the surface level radiation at all these locations. This data we combine with the satellite observation to have regional impact assessment. While talking to the Indian scientific community, especially the students community, I just talk about little bit about how aerosol optical depth can be measured from the ground-based observations. Because some of the engineering or physics students can have can develop some hardware and necessary software, and you can make your own measurements as an exercise. Basically, how we can, one of the simplest way to measure aerosol optical depth is to measure the direct radiation. We know that when we receive radiation at the surface, we receive both the direct solar radiation as well as the diffuse radiation, which is actually after the multiple scattering present in the atmosphere. By reducing the field of view of the receiving optics, we can have direct radiation. In this particular instrument, which has developed in-house at SPL, we receive radiation at around 2° field of view, so that we get the direct radiation. And if we measure direct radiation as a function of time, we can have the measurement of the time information can be converted to the zenith angle. So finally, we get the radiation as a function of direct radiation as a function of zenith angle. The importance of this is actually the zenith angle information can be converted to the relative air mass. We know that when sun is at Nadar, we have less relative air mass, which is we show that m is equal to 1. When sun is at different angles with respect to the Nadar, we have the relative air mass will enhance. When we have the solar radiation, direct radiation as a function of zenith angle, and which we can convert it to the relative air mass, we get an important information using the Langley technique. The Langley is the person which proposed this technique. We can estimate optical depth. What actually we are measuring? We are measuring the solar signal, basically the voltage signal, as a function of solar zenith angle. The solar zenith angle, using this relation, we can convert it into the relative air mass. And when we use the Lambert's-Beer law, which we all use in our many of the scientific applications, when we use it in the atmospheric condition, we can see that the logarithm of voltage versus the relative air mass gives a linear relation. The slope of this linear line gives the total optical depth. And by subtracting the molecular contributions and water vapor contribution, we can calculate the aerosol optical depth. This probably the engineering students can even develop this kind of ground-based system and make measurements on aerosol optical depth, and which you can give important information about the amount of aerosols present in the atmosphere. This we have spread these measurements using this instrument all over the country, and we have a long-term measurements of the columnar content of aerosol. This is very important for climate impact assessment. We found that based on the last 20 years of measurements, we know that the human impact will release so much of aerosols into the atmosphere. We have a trend of an increasing trend, which of course the value is of the order of 0.005 per year. This is one of the important contributions from the ISRO's Geosphere Biosphere program to the international scientific community, that the quantification of the increasing trend in the aerosol optical depth over the South Asian region as a whole, which we shows that the value is very small in a per year cases. But if you look at in a long-term perspective, like in a 40 years time frame, aerosol optical depth can be increased significantly. So these quantifications are very important for the mitigation strategies. So now I will go into the next aspect. We have, along with that, we have surface-based observations. Surface-based observations, like I have mentioned some time back that aerosols are of different type. Aerosol, which are the particles suspended in the atmosphere. There are scattering aerosols as well as absorbing aerosols. But the absorbing aerosols are not through any natural processes. No geosphere process or biosphere process will not produce black carbon. It is basically comes from burning, which is basically an anthropogenic activity. So when we look at the long-term observations of black carbon from some of our ISRO GBP network observatories, we see that there is a decreasing trend, or the trend is, it's not showing an enhancement. This is basically surface-based observations, which shows that the anthropogenic influence from our region is not so a significant kind of situation. But when we look at that, these are all surface-based measurements. In a warming world, these aerosols, probably it can get lifted to the higher altitude due to convections. This is also one possibility. So look into that. We have combined our observations, the surface observations, with the spaceborne observations. See, I have talked about the capability of spaceborne observations. There are international missions which provide very valuable information on the vertical profiles. There is one international mission called the Calypso, which is a LiDAR. We know that radar. In the radar, we use radio waves to probe atmosphere. So similarly, we can use the light waves like a laser to probe the atmosphere. There is a space missions which emit laser beams to the atmosphere, which gives crisscross cut off, the clouds and aerosols, particles present in the atmosphere. Using proper algorithms, we have made an attempt to have the slices of aerosols over the South Asian region. This gives the altitude distribution of the aerosols over our region. We can see that how aerosols are distributed at different altitudes, up to about 5 to 6 kilometers. This gives very valuable information on the distribution of altitude distribution of aerosols. What we found is actually during the pre-monsoon time, the aerosols which are present very close to the surface during the winter, which we used to create winter haze in the northern Indo-Gangetic plain, is lifted to the higher altitude during the pre-monsoon time. These kind of observations are only possible because of the combination of space-based observations with the ground-based observations. Because this shows that during pre-monsoon time, the aerosol system, basically the particle present in the atmosphere, is lifted to the higher altitude over the Indian region. This is actually a blade cut of aerosol vertical distribution over our Indian region. We can see that the surface and the Himalayan averaged out over this region. We can see that a layer of aerosols over the Indian region, which is basically between 2 to 5 kilometers. Initially, we thought that this is what is the type of composition, whether it is relevant for climate. To examine that, the ISRO basically formulated a program called Regional Aerosol Warming Experiment. We made crisscross aircraft observations through this layer of aerosols to understand the kind of aerosol, whether it is scattering or absorbing aerosols. We found that the aerosols over the Indian region, which is lifted to higher altitude, are quite absorbing in nature. This phenomena is basically during the pre-monsoon time. So there is a lot of postulates now. Basically, it is called there is a very strong postulate is actually called the elevated heat pump hypothesis, which shows that this can affect the regional circulation, basically the monsoonal circulation. More detailed studies combining more observations are in progress from the Indian scientific community on this aspect. Coming back to the space missions, when we analyzed these aerosols for its shape, we found that these particles are mostly non-spherical in nature. We always assume in aerosol science that particles are mostly spherical. That is a very important assumption while dealing with aerosol radiation interaction. But when we look at the type of particles present in the atmosphere, we found that there is a significant amount of non-spherical particles also. So this non-sphericity is very important for space-based observations, because the dust particles which emits through geosphere process, basically in the desert region, due to weathering processes and all, which are mostly non-spherical in nature, which we call it as mineral dust. These aerosols, these particles, once it is in the atmosphere, it can have detrimental effect on the radiation balance. But using the LiDAR measurements, which is from the space, using the non-sphericity, which gives very important information on the depolarization of the signals, we can estimate what is the contribution of the dust which comes from desert region to the total aerosol system. And we could estimate that using the space-based observation, which we can see that during winter months, the amount of the contribution of dust to the aerosol system over this region is quite negligible. But during pre-monsoon time, large amount of dust aerosols through emitted over the Saharan region through geosphere processes get transported to the South Asian region. And this is basically the one of the important aspects which is responsible for the layer of aerosols over the Indian subcontinent. So this kind of observations are only possible with the space-based measurements, basically LiDAR observations, which we could, using this observation, we could find out that the dust layer, how far it can go up in the atmosphere. We can see that it can go up to about 5 to 6 kilometers in the atmosphere. These are all very important informations which we can derive by combining the ground-based observations with the space-based observations. Now, because when we do the space-based observation, we know that any space-based, whether it is active or passive remote sensing, the picture which we have shown is basically the active remote sensing, where we have the signals which is from the satellite which goes to the atmosphere and reflected from different or scattered from different layers, which we received with a telescope and determined. So which is called active remote sensing. But there are remote sensing technique where, like a MODIS kind of satellite or Indian Ocean Color Monitor, which is basically the reflected radiation is taken, and through appropriate retrieval technique, we can derive the aerosol optical depth or greenhouse gases, which we call as passive remote sensing. In the whether it is in the active or passive remote sensing, the retrieval techniques are very important. There are certain assumptions are involved. So we need to have ground-based effort to validate this. So these layers of aerosols we have validated with the help of high altitude balloon observations from the AFR balloon facility. We found that the same region where we found the thick layer of aerosols, we can see that there are layers present with the high altitude balloon experiments also. There are some international aircraft missions also which has happened over Indian region, which also confirmed this thick layer of aerosols over our region. This all shows the capability of the space-based missions to address this, different layers also. Now, coming to some of the effects of the geosphere biosphere interaction on the climate, one of the most important aspects is actually which we recently published is actually the fertilizing role of African dust in the Amazon rainforest. This kind of observation studies were possible only because of the space-based observations like Calypso. This was an international study which involves several efforts, scientists from different parts of the country, which they have found that the Amazon region is mainly fed by the Saharan dust. So any changes in the Saharan land use, land cover changes in the Saharan region will have detrimental effect in the Amazon, which is far away, which is actually a different continent. So which shows that The geosphere, biosphere, and atmospheric interaction is a coupled system, which act together, which is very important for the climate system, and which can be addressed only with the help of the combination of ground-based and space-based emissions. So, in summary, what I want to say is actually the geosphere, biosphere, atmospheric interactions play a critical role in shaping the Earth's climate. These interactions involve complex exchanges of energy, water, gases, and aerosols between the solid Earth, living organisms, and the surrounding air, which is the atmosphere. And the essential climate variables, which is actually the reflection of all these processes, which can be measured or observed using the space-based observations of different missions. No single missions can have a complete understanding of the essential climate variables. These essential climate variables essentially determines our the climate state. The understanding of that is very important for any mitigation strategies for improving the sustainable world. So with this, I conclude here. Thank you. I am open for